All right, well, we've arrived at our last section of the course, Math 021, which is going to be section 3.7, dealing with probability. As an introduction to probability, just think about a couple of questions. If I said, what's the probability that the Mets will win the World Series this year, if there is a World Series this year? Or what is the probability your phone will ring today? Or what's the probability that it will rain today? Or what's the probability that it's going to get to 130 degrees outside today? Well, if you're a Met fan, you probably wouldn't say that the Mets have a 90% chance of winning the World Series because you know better. You might say the probability of your phone ringing today is 100%. You might say the probability that it's going to rain today is 20%. Yeah, it looks pretty sunny out. And the probability that the temperature will reach 130 degrees today is 0%. So, what you really should have noticed there is that all those values were somewhere between 0 and 1. Because 90% would be 0.9, 100% would be 1, 20% would be 0.2, and 0% is obviously 0. So a couple of things there to note are that the 100% probability means that it's certain, right? It's definitely going to happen. For me, that's not true because I don't get a lot of phone calls. But if you're a popular person and you get a lot of phone calls, yeah, you could pretty much say that it's certain that your phone's going to ring today. And then the 0% means that it's impossible, right? Because it's impossible to get to 130 degrees. Maybe if you're in Death Valley, it could, but generally it's not going to get to 130 degrees out. So a probability of 0 would mean it's impossible. A probability of 100% would mean that it's certain. But most probabilities are going to be somewhere in the middle, right? So like the chance of the Mets winning the World Series is definitely not impossible, but it's far from certain. And rain, well, yeah, it probably could happen on any given day, but it might not definitely happen. So what probability is trying to do is it's trying to quantify, so basically put a number to uncertainty. So it's a way to quantify uncertainty. So a couple of definitions. So an experiment in probability is basically going to be any exercise or activity that has a specific outcome where you can observe the outcome, and all of the outcomes are going to be known as the sample space, right? So an outcome is kind of like a result of an experiment. So an experiment is any activity that's going to have an outcome, and that outcome is a result of an experiment. So when you're flipping a coin, there's two outcomes, right? You can get a head, you can get a tail. And then when you put all those outcomes together, you get what's called the sample space. So the sample space is just the collection of all possible outcomes of an experiment. And then a tree diagram, this is something that can be used to list a sample space. It sometimes will make it easier to draw a tree diagram if we're going to list the sample space. And then an event is basically just a set of one or more outcomes. All right. So if you take outcomes and put them together, you can form an event. So, like for example, if you're rolling a six-sided die, there's six outcomes, right? One, two, three, four, five, and six. And maybe an event would be getting an even number. So an event would be the outcomes 2, 4, and 6. Right? Another event would be getting an odd number. So the outcomes in that event would be 1, 3, and 5. All right. So if you take some outcomes and put them together, you can form an event. But this set of definitions is important to remember, right? So an experiment, anything that has a result, and those results are known as outcomes. And if you put all those outcomes together, you get a sample space. You can sometimes use a tree diagram to get a sample space. And if you put multiple outcomes together, you can form events. So here's what I just talked about actually. The sample space for rolling a six-sided die, well, there's your six-sided die. So there's going to be six outcomes for it. So what are those six outcomes? The outcomes are going to be 1, 2, 3, 4, 5, and 6. So there's six possible outcomes for that experiment. Now if you're flipping a coin twice, that's one that you could start drawing a tree diagram for, and a tree diagram would look something like this. So okay, like you start at a single point, like kind of like the origin point. So this is like your experimenter. So if I flip the first time, right, flip 1, I could get heads or I could get tails. And then on my flip 2, I could get heads or tails again, but that heads or tails could have come after first getting a head on flip 1 or after first getting a tail on flip 1, right? So if I put all four of these things here now together, there's my four outcomes. So where did this H come from? It came from that H. So the first outcome would have been H, H. This second outcome came from that head also, so that outcome was H, T. This H came from that T having been achieved first, so that was TH, and then this T came after that T had already occurred, so that's TT. So there's your four outcomes in the sample space. And then if you flip a coin 3 times, you can see what happens to the sample space then. So here's a tree diagram for that, already worked out nicely for you. So you can see how it started out the same as my last tree diagram. In my last tree diagram, I ended here, right? I had those four outcomes, but now since I'm flipping 3 times, after all four of those outcomes, I'm going to have two additional. So I end up with a total of 8. So you can see where this head, head, head came from this. Tail, tail, tail came from that, and so on and so forth. So there's your 8 outcomes for flipping a coin 3 times. So eventually, if you do enough of these tree diagrams, you can arrive at what's called the counting principle. And the counting principle pretty much says that if there's a certain number of ways to do one step of an experiment and a different number of ways to do the second step of an experiment, there's going to be m times n ways to do both steps. So like when we just did the flipping of the coin, for flip 1, there were 2 outcomes. For flip 2, there were 2 outcomes. And then for flip 3, there were 2 outcomes. So what did we do? We multiplied 2 times 2 times 2 to get our 8 possible outcomes for flipping a coin 3 times. This kind of thing comes up also like in if you're picking uniforms, right, or picking outfits or whatever you want to call it, right? So this guy needs to wear a uniform to his work. He has 3 different uniform shirts and 2 different uniform pants. So he can choose either a green, a red, or an orange shirt. And then once he's picked his green, red, or orange shirt, he can either pick black or white pants. So there's his tree diagram for this, right? He could wear green, blue, green, white, red, blue, red, white, orange, blue, orange, white. And actually, it wasn't blue, it was black, right? So when I said blue, I really meant black. But those are your 6 outcomes there. And how could you get those 6 outcomes using the counting principle? You multiply number of shirts by number of pants. 3 times 2, and that gave you 6. So that would be your counting principle way of getting the sample space. So quick examples of this again. If Barbara has 6 pants and 5 shirts that she can wear to work, how many different work outfits are possible for her? Well, I usually do what I call slots and choices for this. I say, all right, so I'm going to have a slot for the pants, and I'm going to have a slot for the shirts, and then I just determine how many choices I have in each of these slots. So in the pants slot, I have 6 choices. In the shirt slot, I have 5 choices, and the counting principle tells me that I multiply these things together to get 30 outfits. All right? And then all these are going to be similar. So in the case of this example 6, you need to create a garage door code, and the code is going to have 1 letter and then 3 digits. So what's going to happen is you're going to have a total of, remember my slots and choices? You're going to have a total of 4 slots. You're going to have 1 for the letter, and then you're going to have 3 for the digits. So digit 1, digit 2, and digit 3, right? So I have letter, digit 1, digit 2, digit 3, and then you just need to determine, all right, well, how many choices are there for the letter? Well, there's 26 letters in the alphabet, so there's 26 choices for the letter. And then each of the digits can be anything from 0 to 9 where you can repeat. So each digit slot is going to have 10 choices. And again, counting principle tells me I multiply these. So when I multiply 26 times 10 times 10 times 10, I get 1,000 times 26. So it's going to be 26,000. So there's 26,000 possible codes. And then 7 again is the same idea. You're going to have an entree that you're choosing, a drink, a soup, and a dessert. So those are going to be your 4 slots, right? You're going to have a slot for the entree, for the drink, for the soup, and for the dessert. So there's 5 entrees that you can choose, so that's 5 choices for that slot. There's 7 drinks you can choose, that's 7 choices for that slot. There's 3 soups, so 3 choices for that slot. And there's 2 desserts, so 2 choices for that slot, and then I multiply these. So 210 it gives you. So there's 210 possible lunch options. So that's your counting principle, right? Slots and choices, I think, is the way to go, though. So determine how many slots you have, and then determine how many choices you have in each of those slots. So just wrapping up our discussion of the counting principle and sample spaces, we'll look at a couple more examples here. So one is, how many different 6-digit codes are there to unlock an iPhone? So there's 6-digit codes. So that means you're going to have 6 slots, right? Because your code is going to be 6 digits. So you're going to put 6 slots, one for each digit, and I've labeled them D1 through D6. And then what I do is I determine how many choices I have for each digit. So they don't tell you anything about repeating or not being able to repeat. So if they don't mention anything, we assume that we can repeat the digits. So each of those 6 digits, you're going to have 10 choices for, right? 0 through 9 is actually 10 choices. And then the counting principle tells us that we just multiply these things. So we end up getting 10 to the 6th power, which is actually just going to be a million. So there's 1 million possible iPhone codes, which then should make sense if you think about it, because it's really just asking you how many 6-digit numbers are there, right? And how many 6-digit numbers are there when you count 0? 999,999 plus 0, which is 1 million. Okay, so it does make sense when you think about it. And then, so here they want you to actually list all the outcomes in a sample space. So in this case, we are tossing a coin and then tossing a die, 6-sided die, I guess we'll assume it is. So if I set up a tree diagram for this, again, remember what I do is I start with like an origin. This is kind of like me. And what am I going to do? I'm going to toss the coin, and when I toss the coin, I can get heads or I can get tails. And then after I toss the coin, I toss the die, and with the die I can get 1 through 6, but that 1 through 6 can come after getting an H or after getting a T. And you can see I'm not very good with these tree diagrams. Okay, so what I end up having now is 12 branches here, right? So where did my first branch come from? My first branch came from all the H's. So H1, H2, H3, H4, H5, and H6. And then these ones all came from the T. So then that was going to be T1, T2, T3, T4, T5, and T6. So there's my sample space. And technically these are sets, so they're supposed to be inside braces, but we don't make a big deal out of that in this course, really. The important thing is just being able to list them all, identify them. And how many outcomes are there? Well, there's 12 outcomes. And how could I have gotten that by the counting principle? Well, I would have just realized for my tossing of the coin, I had 2 outcomes. And for my tossing of the die, I had 6 outcomes. So when I do 2 times 6, I get 12. And then one more, we're going to again make a tree diagram for the number of possible outfits. We have a onesie and a vest. There's going to be 5 onesies and there's going to be 2 vests. You're going to have the first branch of your tree is going to be for the onesie, and you're going to have 5 of those, right? So you're going to have a pink option, a blue option, a yellow option, a green option, and a lavender option. And then you're going to choose a vest after that, and there's only 2 options for that, orange or magenta. So we'll call that OM. And what's actually a better idea to do with these in a lot of cases is, as you're making your additional branches, rather than just calling this OM, 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 OM all the way down, what actually helps is if you write the complete outcome, and then it helps you, then you don't have to even do it at the end. So this O here is going to come after the P. So this is really PO. This is really PM, and then this is BO and BM. So then what ends up happening is you get them all done already. So now this is already your sample space, because I've been writing them as I've been doing my tree diagram. So it just saves a little bit of time, right? So that's pink, orange, pink, magenta, blue, orange, blue, magenta, so on and so forth. So we end up getting 10 total outcomes. And how did we get those 10 total outcomes? Well, we had a slot for the onesie and a slot for the vest. There were 5 options for the onesie and there were 2 options for the vest. So 5 times 2 gave you the 10. A lot of times these are easy enough where you don't even necessarily need to draw the tree diagram, but it can be useful for at least organizing all the options.